Let's do an example of a random walk. So in this case, the physics problem that we want to solve is to figure out how long in terms of time it takes for light to escape from the core of the sun. So we're given that the sun's energy is produced in its core by nuclear fusion, and I've drawn the core just as a big red dot over there to the right. So what we're interested in figuring out is if the sun's light is produced there initially, in its core, then how long does it take bouncing around within the sun until it reaches the sun's surface? Now, I didn't worry too much about the scale of the core versus the scale of the surface. We'll do that in a calculation in a minute. But schematically, I just wanted to show you what happens. So light just doesn't leave the core and go directly to the surface of the sun. The sun is very dense, so light can't travel very far before it scatters off of something. That'll change its direction and potentially cause it to bounce back from the way it came. So it's a random walk problem. But as we'll see, the random walk doesn't mean that it'll always end up back in the core. In fact, it can escape, it just takes a while. Let me show you the sort of process that we're going to analyze. So the photon starts at the core and bounces around. This is a random walk simulation that I did where I didn't worry too much about the details of how long this photon was traveling or anything like that. All I did was allow it to travel a certain distance and then randomize the angle at which it was moving, just so that you could get an example of a random walk. Now this one was conducted in 2 dimensions. It can move left, right, or up, down. I didn't worry about going in or out of the screen. Now you can see that the photon currently is pretty far away from the core, but it's not quite to the surface of the sun. So it's just bouncing around a lot, and this happens for a long time. Statistically speaking, you might expect to find it at the core, but what that really means is that about half the time it'll end up to the left of the core, about half the time it'll end up to the right, about half the time it'll be above the core, about half the time it'll be below. Statistically speaking, though, you're actually pretty likely to find it somewhere away from the core, and eventually, like just now, it actually manages to escape the sun. So I stopped running the simulation once it got to that surface point. At that point, the photon would more or less freely stream until it reached whatever observer was looking at it. Okay, that's the process that we're going to model. Now, we're going to do a few simplifications here, so let's get rid of all that. Let's say that the average distance that a photon travels between collisions in the sun is 1 centimeter. That is not a terrible estimate. We'll discuss potential issues with that near the end of the calculation. Speed of light is 3 times 10 to the 10th centimeters per second. That's okay. It is constant outside of a medium. You can imagine it might be a little different inside the sun, but whatever, that's not so bad. Radius of the sun is 7 times 10 to the 10th centimeters. That one's pretty well established. And we're going to treat the motion of the photon as a 1D random walk, so we're going to assume it can just move to the left or to the right to get out of the sun's core. Now, of course, in real life it can move in 3 dimensions. That actually doesn't change the problem too much. If you can understand the physics of a 1D random walk, you can get the physics of a 3D one, no problem. So how do we do this? Okay, well, we're going to start by realizing that the distance we want to travel as an RMS distance is the radius of the sun, right? Because the photon starts in the core, needs to reach the outside of the sun, and if you remember from the lecture notes, the RMS distance is related to the number of times that this thing has scattered this way. So the RMS distance equals the square root of n times delta x over 2. So n is the number of times that this thing has taken a little path. The path itself, delta x, is 1 centimeter. The 2 comes out of the statistics. You don't have to worry about that detail. So if we want to figure out the number of times that this thing has to bounce off of something as it's moving around within the sun to reach a total displacement of 7 times 10 to the 10th centimeters, then we can solve for square root of n. And I just multiplied both sides by 2 and divided both sides by delta x. And now we can substitute in these values, right? So delta x, I just said, is 1 centimeter, and that's 1 centimeter per step. So n will be the number of steps. Well, we solve this, and it's going to be a lot of steps. N equals almost 2 times 10 to the 22 steps. Okay, that is quite a few steps. So that's how many steps it takes, on average, for a photon to get that far away from the center of the sun such that it actually would escape. Let's keep that number up here. That's not the same as how long it takes, because to figure out how long it takes, we need to translate number of steps into a time. Well, that's easy to do. The total amount of time elapsed must be the total distance traveled divided by the speed. Now, the total distance traveled is not the displacement. The total distance traveled takes into account the fact that sometimes the photon goes left, sometimes it goes right, and you have a lot of back and forth motion when you have a random walk problem. To figure that out, though, we know how many steps we took, so we just need to remember that the total distance traveled by the photon would be the number of steps times the distance that it covers per step. So it's going to be 2 times 10 to the 22 steps times 1 centimeter per step. And that's just going to be divided by the speed of light, which again we can take to be 3 times 10 to the 10th centimeters per second. Okay, so let's solve for delta t. Well, we do that, we simplify a little bit, And the number we get is 0.65 times 10 to the 12th seconds. Maybe you don't have a good intuitive feel for how many seconds there are in a year. It's 3.15 times 10 to the 7. So in years, delta t is over 20,000 years. So that's the amount of time it would take for a photon that was scattering around within the sun to go from the sun's core to the outside of the sun. Actually, this is probably even an underestimate. That average distance of 1 centimeter per step is kind of hand-wavy. In fact, there are regions in the sun where a photon would get much, much further and regions where it wouldn't get nearly as far as that. So in fact, we probably actually underestimated it. It probably gets stuck in the regions where it can't move very far for a long time. We may be low by factors of 10, hundreds, thousands even. There's another issue, which is that photon transport in the sun near the core actually does sort of work this way. It's diffusive, photons just bounce around until they get out. But then as you get further out in the sun, convection, a process we encountered earlier in the course, is actually responsible for transporting most of the heat away from the center of the sun at that point. So it's a different process. We would have to model that right. The bottom line here is that obviously photons take a long time to get out of the sun if they're just bouncing around through diffusion. And if it's really random, if there's no bias or anything like that, it takes a really long time for energy to escape from the center of the sun.